Hello, my name is Maria Bachtina, and in this video you will see the presentation of master thesis entitled A Decentralized Public Key Infrastructure for Trust Management in X-Road by Kin-Lon Leung. The thesis is one of the deliverables within the challenge area Security Preservations in Blockchain within the Cybersecurity Excellence Hub in Estonia and South Moravia, in short, CHESS. Our small-scale project within this challenge area is called Automated Trust through Self-Sovereign Identity in the Data Exchange Systems. And in this project, we explore the feasibility of a decentralized approach and distributed ledger usage for organizational identity management in data exchange systems. Based on the example of the X-Road system, we develop a proof of concept and look what are the advantages and limitations of the decentralized approach. So now let's listen to Kin-Lon and see what are the results of his research.
Good morning, everyone. My name is Kin-Lon. Today I'm going to present our work for my thesis titled A Decentralized Public Key Infrastructure for Trust Management in X-Road. Let's begin with our motivation for the study. Public key infrastructure with X509 certificates have been the de facto standard for secure communication over the Internet. However, certificate authority and its certificate status distribution mechanism, such as OCSP, has been suffering from scalability issue and can be vulnerable to DDoS attack and replay attack due to its centralized nature. X-Road, as an example, is a centrally managed distributed data exchange system that depends on PKIX. Within an X-Road ecosystem, members consume and provide service to other members via their self-host or trusted security server, which is responsible for access control and the signing of the message. The dependence on CA and OCSP brings limitations to X-Road. Also, organizations wish to join an X-Road ecosystem has to first obtain certificates from CA for signing and authentication. However, the process can be time-consuming due to the need of manual verification. On the other hand, there is a new identity model known as Self-Sovereign Identity, SSI. In SSI, an entity has sole ownership on the ability to control their account and personal data. SSI brings new standard and specification. One of those specifications is Decentralized Identifiers, DID. A DID is a globally unique persistent identifier created and controlled by an entity without the help of any centralized authorities. The creation of such a DID usually makes use of distributed ledger technologies. At the top right of the slide, you are looking at an example of a DID created on the Ethereum network. From the blockchain, one can resolve the bottom DID document, which contains key material for proving the ownership of the DID. Another standard is verifiable credentials, VC. A verifiable credential is a tamper-proof credential that has authorship that can be cryptographically verified. A verifiable credential can be presented as a verifiable presentation. The separated definition of a credential and a presentation enable features like selective disclosure and zero-knowledge proof, which contribute to a more flexible trust establishment process. These new technologies has motivated us to look for a decentralized public key infrastructure which make use of DID, VC, and distributed ledger technologies to address the limitation PKIX brings to X-Road. For that, we have our research question: how can trust be established between information systems using a decentralized public key infrastructure? The research method we use is design science research method. Its principle is that the knowledge of a design problem and its solution can be acquired during in the building and the application of an artifact. We follow the 7 principles of the method proposed. First, to address the limitation PKIX brings to X-Road, we implement a proof of concept of X-Road with DPKI as an artifact. First, we conduct a literature review to look for related works. We use an iterative search process to refine our design. To ensure the rigor of the research, we define traceable design goals, use case, and requirements. Later, we evaluate our implementation based on those requirements and an assessment model. Our contribution is the application of SSI technologies in data exchange system, in particular XRO, for trust management. Finally, we communicate the research finding through the thesis and this presentation. Our design has 3 goals. The first goal is to increase the degree of decentralization. In the new design, 2 information systems should be able to establish a trusted connection without the help of any centralized service such as OCSP. Second, the new design should provide a more granular access control mechanism, which is attribute-based. This is an improvement comparing to the existing XRO, in which access control is done only based on the identity of the subject. Finally, our new design should support automated member onboarding using verifiable credential. In addition, we define some use cases that describe the expected behavior of the XRO components during the trust establishment process, and we also define some functional requirements that fulfill those use cases. After defining the requirement, we start designing our new architecture. The diagram you're looking on the left is the original XRO diagram, comparing to the diagram on the right, which is the XRO with decentralized public key infrastructure proof of concept architecture. In the original design, centralized OCSP are required to obtain certificate verification status in order to establish a trusted connection. In the new design, all information required for verifying a credential can be obtained in the distributed ledger. Also, in the new design, XRO components are now sitting behind these SSI agents controlled by organizations. These SSI agents implement protocols to communicate with other agents, as well as secure storage of credentials commonly known as wallet. These SSI agents take away part of the responsibility of the original XRO security server. For the implementation, I've implemented an instance of XRO including a security server and a central server in Java. I integrate them with open source technology, including Hyperledger Indy as the distributed ledger, Hyperledger Aries Cloud Agent Python as the SSI agent. We use anon cracks which support selective disclosure and zero knowledge proof as the verifiable credential implementation. We use Aries protocols to communicate between agents for secure connection and credential exchange. Our implementation can be seen on the GitLab link at the bottom. Now for the demonstration, I would like to demonstrate 2 activities on the proof of concept implementation that require trust establishment. The first activities I would like to show is member onboarding, in which an organization sends an onboarding request to central server via their security server. The central server will request the organization to present a business registration credential for onboarding, that is, to join an XRO instance. In the video, you are looking from the perspective of an organization who wishes to join XRO. This is the security server UI. At the beginning, the organization don't have any credential in their wallet. They send the onboarding request, and the request is rejected by the central server. Later, we use a demo-only features to populate the wallet with a business registration credential. And we send the onboarding request again. This time, the request is accepted by the central server, and the date of the newly onboarded member is written on the ledger for discovery. Another activity I would like to show is message exchange between information system of two X-row members. In the video, you are looking from the perspective of a service consumer who wish to consume a service from a service provider. At the top window is the security server, and in the bottom is a terminal which are used to simulate the information system of the service consumer. At first, the service consumer have to obtain the service provider deed from the distributed ledger. Later, the consumer can send a request to its security server proxy API, specifying the service provider deed and the resource path. The two security servers will exchange credentials, and if the credentials are verified, the requests are forwarded and the response is returned. All message exchange records are signed and stored in the SSI agent. The signature is done using the keys that can be found in the member's deed document. For evaluation, we first evaluate our implementation against the functional requirement elicited during the design phase using their acceptance criteria. The results show that our implementation passed all 15 functional requirements. As an example, the first requirement is that a component must present a verifiable credential with a cryptographic proof of possession to create a verifiable presentation. Our implementation used a non-crack presentation which contains a proof of credential holder binding through the use of a linked secret. In turn, our implementation matched the acceptance criterion. Another evaluation we have done is based on the Identity Management System Quality Assessment model. The evaluation results show that the proneness to high-level risk decreased since the use of distributed ledger reduced the load on a single machine. In turn, the security of the system increased. Next, the use of decentralized identifiers reduced the overall time for credential issuance due to key rotation. As a result, the reliability of the system increased. Finally, both organizations' responsibility over credential and control over privacy increased due to the use of SSI credential. To conclude, the answer to our research question, how can trust be established between information systems using a decentralized public key infrastructure, is that decentralized identifier and verifiable credentials can be combined to construct a decentralized public key infrastructure and replace X509 certificates in PKIX for trust establishment between information systems. Decentralized identifiers bind an identifier to public key without centralized registry, while verifiable credentials assert information about the subject of the identifier. Finally, use distributed ledger-based DID and VC implementation to improve the scalability of the system. That's it for my presentation. Thank you for your attention.